Fullerenes are hollow balls of carbon held together by chemical bonds. This is the first one discovered, C60, with 60 carbons, and it forms the shape of a soccer ball with pentagons and hexagons. And these were discovered in 1985 completely by accident. And one of the things that makes them most interesting is they're a form of pure carbon, one of the elements. And prior to this discovery, carbon had been known for hundreds of years only in two forms. Essentially, graphite and diamonds are both pure carbon. So suddenly in the late 20th century, an entirely new form of carbon was discovered. And fullerenes have unusual properties that we'll get a chance to talk about. And shortly after the discovery of fullerenes, yet another form of carbon was discovered, the carbon nanotubes. Here are the different kind of models, which are cylindrical tubes of carbon, hollow down the middle, but all hexagonal arrangements of carbons. And this is a very short one. They grow very long, to many, many times as long as they are in diameter. But these models are large representations of something that are really very, very small. Each of these black things is a carbon atom. And carbon nanotubes are extremely thin. They're 1/100,000th the thickness of a human hair, but they're very, very strong. So they have some very unusual properties, and chemists have gotten very excited about trying to use these new forms of carbon for lots of different applications. Fullerenes were discovered by Harry Kroto, a professor at the University of Sussex, who was visiting Rice University in 1985, doing experiments under high vacuum with graphite and high-powered lasers. And they discovered that if they hit graphite with this high-powered laser, a lot of energy went in, and the graphite was transformed into these balls of carbon. And by spectroscopic methods, they were able to detect them and identify this unusual cluster of 60 carbon atoms, and then later some larger clusters with 70 carbon atoms and even larger. So there's actually a whole family of these things. They were not able to actually isolate and put this stuff in a bottle. They couldn't make enough of it to get their hands on it, so they tried very hard for a number of years to modify these methods to get larger quantities of it, but they were unsuccessful. And then finally, another group of chemists, using a different method for vaporizing graphite, were able to make fullerenes for the first time in quantities that they could isolate. And shortly after that, using the same method, carbon nanotubes were discovered as a byproduct of that synthesis. So these are sort of empirical methods that people stumbled on and discovered by accident that make these balls of carbon and these tubes of carbon. But there was no kind of controlled way of making them. They're just sort of accidents of nature. We got interested in this field. I was fortunate to hear Professor Kroto give a seminar in the late 1980s, a few years after the discovery of C60. And he explained that they were unable to actually make quantities of this that they could isolate. So I began thinking about this as a challenging target for synthetic organic chemistry, which is my field. Could we make these in the laboratory by standard organic chemical reactions, starting from starting materials that we could buy, running chemical reactions to transform them in A into B and B into C and C into D, and eventually at the end we get fullerenes. So we started working in this area back around 1990 to see if we could develop methods for preparing these completely different from the vaporization of graphite. And that's what got us started in this field. When people first discovered fullerenes, they looked at these balls of carbon and thought, what kinds of properties will these have? And one of the first properties discovered was that in the solid state, so if these balls are crystallized, they're just balls sitting next to balls in the solid state. At low temperatures, this solid material will actually conduct electricity, which is unusual for organic materials, which are mostly insulators. And some workers at Bell Lab, now professor at the University of California, Riverside, Robert Haddon, predicted and then demonstrated that if these are doped with certain metals, that the conductivity becomes superconductivity at low temperatures, and that by changing the properties of the doping, they could get materials that were superconducting at higher temperatures than anyone else had ever achieved before. And one of the holy grails in science is to try to develop materials that are superconductors at room temperature. So a superconductor is something that allows you to move electricity or electrons from one point to another point through a wire with no resistance. So with a copper wire, a silver wire, or any of the conducting materials we have now, there's some losses in energy to getting from one place to another just through resistance in the wires. And something like 20% of all the electricity generated in the United States in power plants is lost through just transmission. So when electricity is generated, say, in a coal-fired power plant in Arizona, and the electricity is sent to Los Angeles to light the light bulbs in Los Angeles, only 80% of the electricity actually makes it there. And that's just a huge amount of waste of electricity just moving energy from one place to another. It's more than we spend on importing oil from around the world. If we had superconducting wires instead of regular wires, we wouldn't waste all this energy. So there's a big interest in developing room temperature superconductors. Fullerenes are one of the things that are getting us closer to that. Fullerenes are also being used in organic solar cells. So the solar cells that are used on things like our pocket calculators, for example, so that we don't need batteries, or on satellites that circle the Earth, they get their energy from the sun through silicon-based solar cells. There's a new development in chemistry to try to develop organic materials that can be used as solar cells, and they're not as good yet as the silicon solar cells, but fullerenes are central to the composition of the materials used for making organic solar cells. These will be flexible and transparent. They'll have completely different properties from the silicon-based solar cells that we're seeing now. But there's a plant that Mitsubishi built in Japan, which now can manufacture C60 on a scale of 40 metric tons a year, in anticipation of being able to use these in all kinds of industrial applications. Marina Petrokina is a professor at the University of Albany, State University of New York in Albany. And when she started there as an assistant professor, she contacted me about our work in these curved molecules because she wanted to try to make transition metal complexes of them. So we started a collaboration in which we would send compounds to her and she would do chemical reactions on them, and we published a number of papers together in the early, just after 2000. And as we got more and more involved in this collaboration, other people started working in this field as well. We decided it would be appropriate to organize a symposium, a one-day symposium on this field, and invite all of the people around the country who worked in this area to a single site. And we did this at the Philadelphia meeting of the American Chemical Society in 2008. And got sponsorship from the American Chemical Society for this. And it was a successful symposium where there were talks all day long, and posters and contributed talks and invited talks. And a few weeks after the symposium, we were contacted by Wiley Publishing saying, we think you should edit a book in this area. You could get all the contributors to write up their presentations as chapters in the book, or you could invite other authors from other parts of the world who weren't able to come to the conference to write chapters. And we talked about it and agreed, okay, we'll do this. And we did. Some of the chapters in the book were written by people who gave talks at this symposium. Others were from Japan, Germany, Israel, all over the world, other contributors to this area. And that came together and makes up the chapters in this book. The general organization of the book is it's both fullerenes and nanotube fragments. The fragments of fullerenes have this sort of geodesic curvature to them, the bowls, whereas the carbon nanotubes are cylindrical, so short section of a carbon nanotube would be a belt of carbon atoms. And we've collected all the sort of geodesic parts in the front few chapters of the book and all the things related to nanotubes near the back part of the book. But then another theme that spans both of these are metal complexes. So the subtitle of the book has something about and their metal complexes. So Marina and other investigators like her have figured out how to decorate these molecules with metals or clusters of metals, and this affects their properties also. So there's some aspects of some of the chapters that deal with that chemistry. Chapter 9 is a chapter that I wrote with three of my former co-workers, James Mack, who was a postdoctoral research associate, Tony Anthony Belanger, who was a PhD student, and Catherine Maricha, who was an undergraduate here. And all three of them worked on a single project. It started with James Mack around 2000. I think he came here as a postdoctoral fellow after completing his PhD at the University of New Hampshire. And Catherine Cat started working with him as an undergraduate, as a sophomore in my group. And then when he left to take a job, she took the project over and worked independently on it. And the next year, Tony started graduate school, and he joined her. And then when she graduated, he took the project over and carried it on, and it became his PhD thesis. So this chapter is really it's a write-up of his PhD thesis, which had never been published anywhere else. So it's the first contribution on his work out of this. I'm really proud of all three of these students. James is now an assistant professor, now tenured associate professor at the University of Cincinnati, and Kat is just completed her PhD at Harvard and is now a postdoc at MIT. And Tony's working for a company in Maine as a synthetic organic chemist. So it's nice to see them all go off to other places. Professor Kroto, as I said, was the one who discovered fullerenes in 1985. It was really the beginning, the birth of this whole new branch of chemistry. And he later shared the Nobel Prize in 1996 for this discovery with the two scientists at Rice University whose lab he was working in as a visiting scientist and whose equipment he was using. They, of course, got very involved in this chemistry as well. And for me, Harry Kroto was inspirational in part because of this lecture I heard in 1989 that got us started working in the area. At the time, he was a professor at the University of Sussex. He has since moved to the United States. He's now a professor at Florida State University. He has also since been knighted by the Queen of England, so he is now Sir Harold Kroto. And he was kind enough we've corresponded a lot over the years, and he has visited Boston College and given a lecture here. And I've visited Florida State and lectured there, and he was kind enough to agree to write the foreword to the book. Well, when we started, there were no methods known for making these curved surfaces of carbon atoms, so there was no way to build in the laboratory a complete ball. So we developed some methods for making these curved, what have become known as Bucky bowls, and then larger pieces. And eventually, about 10 years after we started, we completed a synthesis of the C60 ball, and we published this in 2002 in Science. And we have moved from the challenge of trying to synthesize buckyballs to now trying to make carbon nanotubes. So trying to make pieces like this, which then might be grown into longer tubes, ultimately into full-length carbon nanotubes by chemical methods in the laboratory. So most of our focus these days is on trying to tie up carbon atoms into preformed templates that could be used maybe like a seed from which to grow larger carbon nanotubes. One of the challenges here is that although carbon nanotubes can be made by some of these high-energy processes, the nanotubes that are obtained come in all different sizes and styles. Some of them are this diameter, some are bigger diameters, some are smaller diameter. Some of them have the six-membered rings oriented in a sort of spiral staircase like this one. Some of them, they're not. There's no helical twist to them. Some of them have tubes inside of tubes inside of tubes, so all these concentric tubes. And what scientists and nanotechnology people want is all the tubes to be the same, so that they have the same properties rather than having mixtures of different kinds. So I think of it like all the different kinds of pasta that you can see on the shelves, where there's swirls and there's shells and there's long tubes and stuff like this. If you dumped all of those into a basket together, it would still taste like pasta, but they're all different from each other. And different pasta has different purposes, and different nanotubes have different purposes. Some nanotubes will conduct electricity like wires, and some won't. So if you want to use these as nanowires that are really, really thin and really, really strong, you have to have pure samples of just the ones that are conductive, uncontaminated by the ones that are not conductive. So this is the challenge we're trying to meet. Well, I think the challenges on the horizon for fullerenes are how to modify their properties in such a way as to increase the efficiency of the solar cells that are being made using fullerenes as the electron carriers. In the carbon nanotube business, the big challenge for almost since the discovery of carbon nanotubes is how to get separated pure samples of all nanotubes of one type over here and all nanotubes of another type over there. It's been almost 20 years since they were first discovered, and still today there is no efficient way to separate the mixtures that are made by the traditional methods, and which is what has driven us to try a completely new way of synthesizing them that just doesn't make the mixtures right from the beginning. You make just the kind that you want. And we're partway along in that. The big challenge, and we've made, and other people have started making now, templates, so pieces of fullerenes that look like, or of carbon nanotubes that look like they should serve as templates from which we can grow. So that the last challenge is now developing the chemistry for adding the carbon atoms in such a way that the diameter is fixed and the orientation of the rings is all fixed. This cover is taken from a 19th century painting by the French artist William Adolphe Bouguereau. He called this the knitting machine. It's a young woman who's knitting a scarf. And one of the authors of our chapter in our book, Rainer Herges in Kiel, Germany, saw this as an opportunity to demonstrate the difficulty of synthesizing carbon nanotubes. And he had the image digitally modified, so if you look closely, it's no longer a scarf, it's actually a carbon nanotube where she's putting together the nanotube one ring at a time, one six-membered ring at a time. And so this is one method of making carbon nanotubes. We hope it won't be that laborious to make them in the laboratory, that we'll be able to make them in a more automated way by chemical methods. But we thought this would be a unusual cover for a science book and will stand out on the shelves at American Chemical Society meetings.